In this video, we're going to talk about operations we can do on matrices. So we've already defined what a matrix is. We know a matrix is just a grid of numbers. And we've also talked about a special kind of matrix that we can use to represent a system of equations called an augmented matrix. So now we want to talk a little bit more about matrices in general. Matrices can be used in other situations other than just to represent a system of equations. So since we want to be able to use matrices to represent our applied situations, we need to be able to manipulate them just as we do constants, expressions, and equations, in other words, algebraically. So the operations we can do on a matrix include addition, subtraction, and then actually two different types of multiplication. So we can multiply a matrix by a constant, in other words, by a fixed number, and we can also multiply two matrices together. So we're going to look at both of these types of multiplication. Whenever we want to add and subtract two matrices, they have to be the same size. In other words, we look at the dimensions and the dimensions have to be exactly the same. Otherwise, addition and subtraction are not going to be defined. So adding, subtracting matrices is really simple. To add or subtract them, we're just going to add or subtract the corresponding elements in the matrices. In other words, when we compare the sizes, compare the dimensions, we're also comparing the location of the elements. So we're just going to add or subtract the elements that are in the same location within the two matrices. So for the first example, we've got two matrices. Notice they're both 2 by 3, so they're the same size, which means that if we want to add them together, that operation is defined. So in order to add these two matrices together, we're going to match up the elements that are in the same location within the two matrices, and we're just going to add the individual elements together. So for instance, in the first matrix, the first entry is a 2. And in the second matrix, the corresponding element is going to be a 3. So if we're going to add these two matrices together, I'm going to take the 2, I'm going to add it with the 3, and that's going to be the corresponding element in that particular location in the resulting matrix. So 2 plus 3 gives us a 5, so that's going to give us a 5 in that location. I'm going to do the same thing for all the additional elements in the matrix, and notice that the answer is also going to be a matrix of the same size. So if we add a 2 by 3 to another 2 by 3, the result is going to be a 2 by 3. Same kind of thing if we want to do subtraction. So notice both of our subtracted matrices are going to be 3 by 2 matrices. So I'm going to match up the elements in the same location. So the first element in the first matrix is going to be a 3. The corresponding element in the second matrix is going to be a -2. So I'm subtracting those two elements together. Now the one thing we want to be careful about with subtraction is of course sign issues. So for those two elements, notice it's a 3 minus a -2, so it ends up resulting in addition. So 3 plus 2 ends up giving us 5. Whereas for instance, if we went to the next element, the next one on the row, -2 minus 2 would give us a -4, so it results in just normal subtraction. So we do that for all the corresponding elements in our two matrices, and again, we end up with a matrix of the same dimensions. So we're subtracting two 3 by 2 matrices. Our answer is also going to be a 3 by 2 matrix. Now let's look at constant multiplication. So essentially, like with addition, subtraction, we're just going element by element. So once we're multiplying the matrix by a particular constant, we're just going to multiply each element in the matrix by a constant. So for our example, we have -2 times a 3 by 3 matrix. So we're just going to take each element in that 3 by 3 matrix and multiply it by that constant -2. Now again, we just have to be careful with our signs. So remember, a negative times a positive is going to give us a negative output, and then a negative times a negative is going to give us a positive output. So if we were to go across the top row, -2 times 3 is going to give me a -6. -2 times -1 is going to give me a +2. -2 times 0 is going to give me 0, and then so on and so forth for the second and third rows. And again, notice if we start by a 3 by 3, we end up with a 3 by 3 matrix as well. So how might we use these operations in an actual applied situation? Well, let's look at an example. So our example says, Ms. Smith and Mr. Jones are salespeople at a new car agency that only sells 2 models. August was the last month for this year's models, and next year's models were introduced in September. Total dollar sales for each month are given in the following table. So we have a table. Notice it's broken down by August sales, by September sales, and then further from there we have the compact model car, we have the luxury model car for each of those months. And then across the rows, we've broken it down by salesperson. So the first row represents sales for Ms. Smith, and then the second row represents sales for Mr. Jones. So Ms. Smith, compact sales and luxury sales in August, and then Ms. Smith, compact sales, luxury sales in September. So you get the idea. So technically we don't have a matrix yet, but because we have, essentially we can think of it as a spreadsheet, a grid, this could easily be translated into a matrix. So the first thing we want to do is we want to represent each month's sales by salesperson and by car type as a matrix. So based on how this grid is already filled out for us, it makes sense for the rows to represent the salesperson and then the columns to represent the type of car. And keep in mind, since we're talking about essentially apples to apples, once we write one matrix, we want to make sure that we structure the other matrix the same way. So the matrix for August is going to have Ms. Smith's sales across the first row, Mr. Jones' sales across the second row, and then when we write the matrix for September, we want it to be structured in the same way. So for August, Ms. Smith sold $54,000 worth of compact vehicles and then $88,000 worth of luxury vehicles. So the first entry in the August matrix is $54,000, second entry is $88,000. Mr. Jones sold $126,000 in compact vehicles and nothing in luxury. So $126,000 and zero for our second row. And then same thing for September. So notice sales went up in all categories. So compact cars and luxury for Ms. Smith, and then compact cars and luxury for Mr. Jones. So we have two matrices. Notice these are both 2 by 2 matrices. So what we know from that is that addition and subtraction, if we wanted to add or subtract these two matrices, addition and subtraction would both be defined because these two matrices are the same size. Okay, so the next question. What were the combined dollar sales in August and September for each salesperson and each model? What I'm looking here is the word combined. Combined tells me I'm somehow putting things together. So what we want to know is in total, how much did each person sell in terms of the two different types of cars? In other words, the compact model and the luxury model. In this case, we can represent that by a matrix addition. So if we take the August matrix, take the September matrix, keeping in mind that these two matrices are structured the same way. So the first entry is going to be compact sales for Ms. Smith. Same thing for September. The first entry is going to be compact sales for Ms. Smith. So if I were to add these two matrices together, based on the fact that each of the elements represents the same thing, then I can come up with the total sales across the 2 months. So if I add the first two entries together, 54,000 plus 228,000, I end up with a total of 282,000. So that represents compact sales for the salesperson, Ms. Smith. So on and so forth for all the other elements. So 88,000 plus 368,000, well, that's going to be luxury sales for Ms. Smith because it resulted from Ms. Smith, luxury sales, Ms. Smith, luxury sales, and then same thing for the bottom rows. So 126,000 plus 304,000, and then 0 plus 322,000 gives us the total sales for Mr. Jones. So this is just a compact way of organizing this information based on the question that we were asked. Let's look at another question based on these matrices. Now we want to know what was the increase in dollar sales from August to September. So if you look at the numbers for September, notice they're quite a bit higher. We actually increased sales in every category for both of the salespeople. So when I'm looking for increase, I'm thinking difference. What's the difference in the amounts? Difference is represented as subtraction. I want to take the larger elements and subtract the smaller elements. In other words, larger minus smaller, what was the increase between the two? So in that case, I want to take September sales and I want to subtract August sales. So you'll have to flip back over and look at this for just a second. But we're going from September to August. We're subtracting the September matrix minus the August matrix. Again, element by element. So 228,000 minus 54,000 is going to give us 174,000. So that represents how much change there was in Miss Smith's sales of compact cars. Same thing for the other three elements. So 368,000 minus 88,000, that's going to be how much Miss Smith's sales of luxury cars increased. 304,000 minus 126,000, that's going to be Mr. Smith, or not Mr. Smith, Mr. Jones' increase in compact sales. And then 322,000 minus 0, that's going to be Mr. Jones' increase in luxury sales. So if we were to do all of those subtractions, that tells us what the change is in total from August to September based on the type of car, based on the salesperson. Okay, so let's look at one more question. If both salespeople receive 5% commission on gross dollar sales, we want to determine the commission for each person for each model sold in September. Okay, so notice now we're not talking about a comparison. It's not August to September. It's not a difference. It's not a total. We're just looking at September. So we're only going to use the matrix representing September sales. Now, when I see 5% commission, think 5% commission of sales. The word of mathematically means multiply. So if it's a percentage of sales, that means we have to multiply that percentage by the total sales. Now, algebraically speaking, we can't use a percentage, so 5% cannot be used algebraically. We have to convert it to a decimal before we can actually use it algebraically. So I'm going to convert 5% to a decimal, which results in 0.05. So it's 5% of our sales in September. So it's going to be the decimal version of our percentage, which is 0.05, multiplied by our total sales. In other words, by our matrix for September. So in this case, this is just constant multiplication. So we're taking each of the entries in September. So compact sales, luxury sales for Miss Smith, for Mr. Jones. And we're multiplying each of those entries by 0.05, which is the 5% commission rate. So if I were to take the matrix for September, here's our original matrix for September, multiply each of these elements by that percentage, by 0.05, the decimal version of our percentage, then I end up with the matrix representing our commission. So it's broken down by type of car, by salesperson. So what if instead we wanted to know the total commission for each of our salespeople? Well, we could start it out the same way. This is going to be the individual commission amounts. If we were to take each of the elements in each row and add them, in other words, take 11.4 and 18.4 and add them together, that would be the total commission that Ms. Smith made. If we took 15.2, 16.1, added those together, that will be the total commission that Mr. Jones made. So just a few examples of how we might actually use these kinds of operations in real life. Keep in mind there are certainly different ways we could handle a situation like this, but the benefit of using a matrix is it kind of condenses the information into one particular structure. So you can manage a bunch of different information at the same time and keep it all organized pretty well. Okay, so we've talked about addition, we've talked about subtraction, and we've talked about constant multiplication. The last operation we're going to look at is matrix multiplication. In other words, multiplying matrices together. So the simplest matrices to multiply together are going to be a row matrix and a column matrix, specifically in that order. So a row times a column we can do. As it turns out, a column times a row in that order is actually not going to be defined. So we'll talk about why that is in just a minute. But row times column, that's where we're going to start. So this is going to look a little bit unique. We're going to do multiplication, but we're also going to end up doing some addition. So to multiply our row by our column, we're going to take all of the elements along the row. In other words, start across the row, start on the left-hand side of the row, go left to right. And we're going to take each element across the row and multiply it with the corresponding element going down the column. So in other words, across a row and down a column. We multiply across the row, down the column, and then we take the result of that and we actually add the result together. So we'll look at some numbers in just a second. Hopefully that'll make more sense. But across the row, down the column, and then add. Now, The definition for this doesn't depend on the matrices being the same size. As it turns out, in most cases, they won't necessarily be the same size, but the matrices must have the same number of elements. So in other words, we couldn't multiply a row matrix with 3 elements by a column matrix with 4 elements. That would not actually be defined. So let's look at a couple examples. Let's see why these are defined. So our first one, we have a row of 3 elements, a column of 3 elements. So because these two matrices have the same number of elements, this particular multiplication is defined. So a row times a column. So this is how this is going to work. I would take 2 fingers and do this with 2 fingers. So I'm going to trace through with my fingers what's actually happening. So I'm going to start with the first element in the row. And that first element in the row is actually going to be multiplied by the first element in the column. So just those 2, I'm going to think of those as corresponding elements. I'm going to multiply those 2 together. So 2 times -5, I'm going to multiply those together. That's going to be part of my answer. Okay, then I'm going to go along the row to the next element and down the column to the next element. So that brings me to a -3 and a 2. I'm going to multiply those together as well. So -3 and 2, that's also part of the answer. And then I'm going to go along the row to the last element, down the column to the last element. So I have a 0 times a -2. That's going to be the last part of my answer. So notice we did 3 multiplications. So first elements, second elements, third elements, and I'm going to take all of those resulting multiplications and I'm going to add those results together. So my first multiplication was 2 times -5, which gives me a -10. My second multiplication was -3 times 2, which gives me a -6. And then my third multiplication was 0 times -2, which gives me 0. So -10 plus -6, well, that gives me -16, plus 0, which of course doesn't change anything. So -16 plus 0 is going to give us -16. So that's going to be our answer. Now notice the answer is not just -16, it's actually a matrix containing the element -16. So when I go across the row and down the column, it results in a single number as the final answer, but it's actually a matrix with that single element. So as we expand this idea of multiplication into larger matrices, we may end up with more than one answer at the very end, but it's going to be more than one answer contained in a matrix, and it's going to be a matrix of a very specific size. So across the row, down the column, do all the corresponding multiplications, add the results together, and then that's going to be included in our actual answer matrix. So let's look at another one. So this one is going to be a row with 4 elements, a column with 4 elements, same number of elements, so we know it's defined. So -1 times 2, first multiplication, first element in the row, first element in the column, -1 times 2. Then we have 0 times 3, so that's going to be the next part. 3 times 4, that's going to be the next part. And then 2 times -1 is going to be the last part. So I have a total of 4 multiplications. I'm going to take the product, the result from each of those multiplications, and I'm going to add all of those results together. So my first multiplication gives me a -2. My second multiplication, 0 times 3, just gives me a 0. So -2 plus 0 is going to be -2. My next multiplication gives me a 12. So I have a running total of -2. I'm going to add on 12, so that's going to give me a +10. And then my last multiplication is going to give me another -2. So I've got that total so far of +10, add on a -2, and that's going to give us a +8 at the very end. So again, notice it's a single element, but it's a single element in a matrix. So across that row, down that column, we get a single element, but it's a matrix with a single element. So now we want to expand this. It's not just rows and columns all the time. What if we have matrices that look like these? What if we have matrices that have rows and columns? We need to be able to define multiplication for those, and as it turns out, we can. We're just going to have to be careful as we do this. Okay, So here's how we're going to define it. So we're going to let A be an A by B matrix. So A cross B, that's going to be the dimensions of matrix A. We're going to let matrix B be a C cross D matrix. So C and D are the dimensions of matrix B. So the matrix product of A and B, denoted AB, in other words, we're just multiplying them together, this will be defined. In other words, we can actually find this, we can do this operation if and only if the dimensions B and C are the same. So what does that mean? Well, here are the dimensions for matrix A. Here are the dimensions for matrix B. We're multiplying these two matrices together. What I'm interested in terms of determining whether or not we can actually do this problem is the interior dimensions. So imagine taking those two sets of dimensions and pushing them together. I have A, I have B, I have C, and then I have D. What I'm interested in is the two inner dimensions. So I have the B on the inside, I have the C on the inside. The multiplication of these two matrices will only be defined if those two numbers are the same. In other words, if B and C are the same number. If they are different, matrix multiplication is not actually defined for these two matrices. And we're also going to have to be careful about ordering. So when we multiply two matrices together, it's not commutative. We can't do matrix multiplication in separate orders in general. So the order we multiply the matrices together in matters. So we're looking at those two inner dimensions. As long as they're the same, then we know our matrix multiplication will be defined. We can actually find the matrix product. What are we going to get as our answer? Well, as it turns out, we're comparing those two inner dimensions to make sure that our matrix multiplication is defined. The answer is actually going to have the outer dimensions. So B and C, those are the ones we're comparing to make sure that the multiplication is defined. The remaining two numbers are A and D. Those are the outer dimensions. So we're comparing the inner dimensions. The outer dimensions are actually going to be the dimensions of the answer. So it's going to be an A cross D matrix when we multiply. In other words, there's going to be A rows by D columns, and that's going to be the size of our resulting matrix. Notice that's probably not just going to be a single row, a single column. It's probably going to be multiple rows, multiple columns. We'll have to find each of those individual elements in that matrix in essentially the same way we did it with the individual row and the individual column. We'll go across a row, down a column. That results in a single element. It just means we have to do it multiple times if we have a larger matrix. So that particular operation we did, we're going to do essentially the same thing, but again, we just have to do it multiple times. So we're going to go across each row, and we're going to go down each column. And exactly what we did with the row and column, we're going to do here. So we're going to do multiplication for the corresponding elements along the row and down the column, and then we're going to add all of those individual products together. And we're going to do that same operation, that same sequence of operations for each possible pair. In other words, each row and each column that could match together. So let's look at a general example. Notice this doesn't have any numbers. We don't need numbers at the moment to define what we're trying to do. So our matrix that we're starting with is a 2 by 3. The matrix we're multiplying by is a 3 by 2. Well, how do we know we can multiply these together? It's because the inner dimensions are the same. So 2 by 3, 3 by 2. It's the fact that the 3's are the same. So those are the inner two dimensions. We have a 2 by 3, a 3 by 2. Because those inner dimensions are both a 3, that tells us that this matrix multiplication is defined. We know the size of the result based on the remaining dimensions. So 2 by 3, 3 by 2. The outer two dimensions are 2 and 2. So that tells us the result of our multiplication is going to be a 2 by 2 matrix. So a 2 by 2 matrix has 4 elements. What that means is this row times column operation that we have to do, we're going to have to do that 4 times in order to find the 4 different elements in our actual resulting matrix. So again, the operation is the same, across the row, down the column. So I'm going to start with my first matrix, first row. I want to go across the row and then down the first column. So I would take each of those matching elements, each of those corresponding elements, multiply them together, and then remember we take those results and we add them together. So the first row combined with the first column gives us the first row, first column in our resulting matrix. So we would take all of those corresponding elements, multiply them together, add up all those products. The result is going to be in the matching row and column based on what we multiplied. So first row, first column, first row, first column. Then I'm going to go first row by second column. So we already used the first column, that part's done. Now we need to do first row, second column. So first elements, second elements, third elements. Multiply all of those together. Add the results. It was the first row by the second column. So the answer to that multiplication and addition goes in the first row and then the second column. So wherever those two intersect. So notice that's going to complete the first row. And it also means we're done with the first row in terms of our multiplication. So as we continue on, now we're using the second row. We've combined the first row with both of our columns. Now we need to combine the second row with both of our columns. So second row across the row and then down the first column. So first elements, second elements, third elements, add them together. Second row, first column goes to second row, first column in our resulting matrix. So all of those products, add them together. The result goes as that entry into our answer matrix. And then last but not least, second row, second column. So we multiply our three elements together, we add them. Second row, second column takes us to the second row and then the second column in our answer matrix. So all four of those operations, if we put those together, those each give us one of the four parts of our resulting matrix. Once we're done with that, that gives us the full answer for our problem. So the matrix we end up with after we do all those operations, that's going to be the actual answer for our matrix multiplication. Okay, so let's try a few. Let's look at some actual matrices. Number one, once we want to multiply, we have to determine whether or not the multiplication is defined. But if we know it's defined, what do we do from there? So let's look at some examples. Okay, so we've got an A, a B, and a C matrix. A is going to be a 3 by 2, B is going to be a 2 by 4, and then C is going to be a 2 by 2. So the first multiplication we want to do is A times B in that order. So first thing I want to do is compare the dimensions. I have specific dimensional requirements in order to determine whether or not A times B is actually defined. So A is going to be a 3 by 2, B is going to be a 2 by 4. I'm comparing those inner two dimensions. So the inner dimensions, notice they're both a 2. It doesn't matter specifically that they're 2, it just matters that they're the same. So because both of those inner dimensions are the same, automatically that tells me A times B is defined. This is actually a pair of matrices that we can multiply together, at least in this order. The result of that multiplication is going to be the remaining two dimensions, the ones we didn't compare, those outer two dimensions. So the outer dimensions are going to be a 3 and a 4. So that tells me the resulting matrix that I get after I multiply is going to be a 3 by 4 matrix. Okay, so I'm going to set up the multiplication. I want to write down each of my matrices. So it's just copy and paste, just writing down each of those matrices, again, in that order. It's got to be in that order. And we know the result is 3 by 4. So I can draw a 3 by 4 grid. You can actually draw lines across the grid if you need to help yourself fill it in and stay a little bit more organized, but that's not necessary at all if you don't feel like doing that. It's just a way to help you stay organized. Okay, so we start with the first row. So we're going to go row by row by row, and then column by column by column by column. So 3 rows, 4 columns, 3 rows, 4 columns. So I'm going to start with the first row in A, and I have to combine that row with each of the columns in that second matrix. So I'm going to start with the first column. So I'm going to go element by element across the row and down the column. So my first pair is 2 times 1. So 2 times 1 is going to give me 2. My next pair is 1 times 2, which is also going to give me a 2. So 2 times 2, or excuse me, 2 plus 2. There we go, that's better. I'm going to add those together. So add those two products together. 2 plus 2 is going to give me a 4. So first row, first column, first row, first column. The resulting element is a 4. Okay, so I've used that first column. I'm still using the first row, but now I go to the next column. So 2 times -1 is going to give me a -2. 1 times 1 is going to give me 1. So -2 plus 1 is going to give me a -1. And notice as I keep using the row, I keep filling across the row. So just keep in mind, as you continue along that one row, continue to use that row, you're just filling across the row in your answer matrix. So our next entry is going to be a -1. Now I'm going to go to the third column. So 2 times 0, 1 times 2. 2 times 0 is 0, 1 times 2 is 2. 0 plus 2 gives me a 2. Now I go to the fourth column. 2 times 1 is 2. 1 times 0 is 0. So 2 plus 0 is going to give me a 2. So I filled in that whole row, and notice that also I've used that first row with each of the 4 columns. So that means first row, I'm done with that, and I filled in the first row on my matrix in its entirety. Now I'm going to go to the second row. So 1, 0. And then I have to combine that with each of the 4 columns in the second matrix. So second row, column by column by column by column. So 1 times 1 is going to give me 1. 0 times 2 is going to give me 0. 1 plus 0 gives me 1. And notice where it goes. It goes as the first entry in the second row. So now I'm using the second row. I'm filling across the second row. So my first entry is that result, which is going to be 1. Now I'm going to go to the next column, but I'm still in row 2. So 1 times -1 is -1. 0 times 1 is 0. So -1 plus 0 is going to give me -1. Now I'm going to go to column 3. 1 times 0 is 0. 0 times 2 is 0. 0 plus 0 is going to give me 0. And then the fourth column. 1 times 1 is 1. 0 times 0 is 0. 1 plus 0 is going to give me 1. So that fills in the second row. Now I'm going to go to the third row, combine with all 4 columns, which will fill in the third row in our answer matrix. So -1 times 1 is -1. 2 times 2 is 4. -1 plus 4 is going to give me 3. -1 times -1 is +1. 2 times 1 is 2. So +1 plus 2, also going to give me a 3. -1 times 0 is 0. 2 times 2 is 4. So 0 plus 4 is going to give me a 4. And then -1 times 1 is -1. 2 times 0 is 0. So -1 plus 0 is going to give me -1. And notice when we finish with the last row and the last column, we're filling in the very last element in our final matrix. So once we do all of those operations in sequence, that is going to be the resulting matrix. So that 3 by 4 matrix is going to be the product of A times B. Okay, so let's look at another one. So we did A times B. Now what about B times A? So it's the same matrices, but now they're in the opposite order. Again, I've got to start with dimensions. So I want to know, is this multiplication even defined? And I have to base that on my dimensions. So B, we determined, is a 2 by 4 matrix, and then A is a 3 by 2 matrix. So I'm going to compare those two dimensions together. I'm looking at the inner dimensions specifically. So my first inner dimension is a 4. My second inner dimension is a 3. So notice in this case, those two inner dimensions do not actually match up. So because they don't match up, because they're not the same, the multiplication B times A is actually undefined. Those two matrices cannot be multiplied together in that order. So just because A times B was defined does not mean that B times A was defined as well. So multiplication of matrices is a little bit different than just standard algebraic multiplication of numbers, variables, expressions, anything like that. In those situations, we can multiply in any order and it doesn't change anything. Matrix multiplication does not work the same way, just based on how we define the actual individual multiplication operations. So in this case, this particular matrix multiplication is not defined. Okay, let's look at a couple more. Now we want to do B times C. So let's flip back over, let's look at those. So B times C. So B is going to be a 2 by 4. C is going to be a 2 by 2. So let's go compare those dimensions. 2 by 4, 2 by 2. Same problem as with the last one. So notice those inner two dimensions, that 4, that 2, those don't match up. Because those don't match up, that means B times C is actually undefined. Now what if we flip the order? What if it's C times B? So that would be a 2 by 2 multiplied by a 2 by 4. I compare those inner two dimensions. Now they're the same based on the order I did that in. So that means the result is defined and it's going to have the remaining two dimensions defining it. So it's going to be a 2 by a 4 matrix. So 2 rows, 4 columns. So I'm going to take my C, I'm going to take my B. Again, this is just copy and paste, just copying those two matrices from the previous page. And I want to multiply to give me that remaining 2 by 4 matrix. Now, one thing I want to point out here that's kind of unique. Notice the actual dimensions for the final matrix match the dimensions for one of the matrices we started with. But if you look at the multiplication we did before, the other one that was actually defined, we had a 3 by 2 and a 2 by 4, and it gave us different dimensions entirely. It gave us a 3 by 4. So the resulting matrix didn't actually match either of the two originals. Sometimes it happens this way. Sometimes it happens this way, in that the dimensions actually match. It just depends on what we're starting with. It depends on the matrices we're multiplying together. So there's no way to necessarily generalize this is going to happen in this situation, this is going to happen in another situation. We just have to compare the dimensions and see what we actually get. Okay, so remember, we're going to go across the row, starting with the first row, and then we're going to match it up with each of the 4 columns. So I'm going to go a little bit faster this time. So 2 times 1 is 2. 6 times 2 is 12. 2 plus 12 is going to give me 14. Okay, next column. 2 times negative 1 is negative 2. 6 times 1 is 6. Negative 2 plus 6 is going to give me a 4. Okay, 2 times 0 is 0. 6 times 2 is 12. That's going to give me a 12. 2 times 1 is 2. 6 times 0 is 0. So 2 plus 0 is going to give me a 2. So I've matched up my first row with all 4 columns. That's filled in the entire first row in my answer matrix. So now I can go to the second row. So second row matched with our 4 columns. So negative 1 times 1 is negative 1. Negative 3 times 2 is negative 6. Negative 1 plus negative 6 is negative 7. Negative 1 times negative 1 is positive 1. Negative 3 times 1 is negative 3. Positive 1 plus negative 3 is going to be negative 2. Negative 1 times 0 is 0. Negative 3 times 2 is negative 6. So 0 and negative 6, add them. I'm going to get negative 6. Negative 1 times 1 is negative 1. Negative 3 times 0 is 0. Negative 1 plus 0 is going to give me negative 1. So that's going to be my actual matrix. Okay. Now, with multiplication, we know there are other ways to get multiplication, particularly in special situations. So exponents, for instance, mean repeated multiplication. How do exponents work in a situation like this? Well, they mean the same thing. So for instance, squaring a matrix would mean multiplying the matrix by itself, just like squaring a number. Squaring something like 2 just means multiply 2 by itself, in which case you'd get a 4. But we can square 2 and get 4. We can square negative 2 and get 4. It's always defined. It's not always going to be defined for a matrix. How do we deal with a situation like this? Well, it doesn't matter that we're multiplying the matrix by itself. We started out the same way. We have to determine whether or not that multiplication is defined in the same way by comparing our dimensions. So say we want to do a squared. In other words, we want to take the matrix A and we want to multiply it by itself. So let's flip back over. So our matrix A, remember that was a 3 by 2 matrix. So I'm taking that 3 by 2 matrix and I want to multiply it by itself. So I'm going to compare my dimensions. I'm looking at those inner 2 dimensions. So based on how they line up, the first inner dimension is 2, the second inner dimension is 3. Because those do not match up, this multiplication is not actually defined. So A is not a matrix that we can actually multiply it by itself. So A squared is actually going to be undefined. Now, what about C squared? C was a 2 by 2 matrix. We have a special name for that. That's a square matrix. So if the rows and columns, the number of each are the same, we actually have what's a square matrix. So in other words, you look at the dimensions and the dimensions are square. So it's a 2 by 2 multiplied by a 2 by 2. We compare those inner 2 dimensions. They're the same. Okay, so that tells me this particular operation is defined. We can take C, we can multiply by itself, aka square it. And then my outer 2 dimensions, again, those represent the size of my resulting matrix. So if I multiply a 2 by 2 by another 2 by 2, the result is going to be an additional 2 by 2 matrix. So this matrix multiplication is defined. So I'm going to copy down C and I'm multiplying it by itself. So across the row, down the column for both columns, across the row, and down the column for both columns. So I'll allow you to do this one on your own. You might want to pause the video and just try this one on your own. See if you can get out to these particular elements at the very end. You should get those particular numbers. Again, it's defined because these 2 matrices have the same inner dimensions, and it just so happens in this case that the outer dimensions result in a matrix that's the same size as the original ones we multiplied together. Okay, so that's just a few examples of how we would multiply matrices together. So we looked at a situation where we would use addition, subtraction, and constant multiplication. How would we actually use matrix multiplication? Well, let's look at an example of that as well. Okay, so a nutritionist for a cereal company blends 2 ingredients, we're going to call them A and B, in 3 different mixes. We're going to call them X, Y, and Z. So we're blending ingredients A and B into different mixes, X, Y, and Z. The amounts of protein, carbohydrates, and fat in grams per ounces in each ingredient, remember the ingredients are A and B, so the amount of nutrients in each ingredient, as well as the amounts of each ingredient used in the 3 mixes, are given in the tables below. Okay, so we have 2 tables. So first table, our rows represent nutrient types, and then it's by ingredient type. So ingredient A has protein, carbs, and fat content. Ingredient B also has protein, carbs, and fat content. Our second table gives us the ingredient types in each of the individual mixes. So we can make mix X, Y, and Z from different combinations of our 2 ingredient options, A and B. So in mix X, we have different parts of A and B. Mix Y, different parts of A and B. And then mix Z, different parts of A and B. Okay. So first thing we want to do is take these 2 tables and convert them into matrix form. Again, keeping in mind what each row, what each column represents. So as I write these in matrix form, I want to make sure I know what the different rows and different columns represent. So we'll call the first one matrix M. So matrix M, each of the rows represents a type of nutrient. So protein, carbohydrates, and fat. And then each of the columns represents the type of ingredient. So ingredient A in column 1, ingredient B in column 2. Notice now we have a 3 by 2 matrix, and we started with a 3 by 2 table. Okay, now the same thing for the other table. We're going to call this matrix N. We have 2 rows. Each row represents an ingredient type, and then 3 columns, which give us the ingredient type by mix. So each of the mixtures has a certain amount of ingredient A, a certain amount of ingredient B. Those are indicated by the individual columns. So those are going to be our 2 matrices M and N. Okay, so the question is, we actually have 2 questions. Let's look at them at the same time. So we want to find the amount of protein in mix X, and we want to find the amount of fat in mix Z. So this is actually kind of a layered question. So we have nutrient content per ingredient, and then we have ingredient contents per mix. But we want to relate nutrient content to mix. So specifically, we want protein in mix X and fat in mix Z. So we can't immediately use these individual tables as they're already given. They're not relating the two things we want to relate. Right now we have nutrients to ingredients and then ingredients to mixtures. We want to relate nutrients and mixtures. The problem is we have that barrier in the middle that's representative of our different types of ingredients, which at the moment we're not interested in. We're interested in the other two things that are not being compared. So what we can do is we can potentially multiply these two matrices together, which will give us a resulting matrix that actually relates the quantities that we're interested in at the minute. The question is, though, what order do we have to multiply these matrices in order to get what we want, to get the different information that we're interested in? Well, number one, we need to make sure that we can actually multiply these matrices together in either order. If neither of these multiplications is defined, then we couldn't actually use matrix multiplication to answer this question. So first thing we want to investigate is, are the two different orders for matrix multiplication defined in this case? So M times N, M is 3 by 2, N is 2 by 3. So I'm comparing my dimensions. The inner dimensions are the same. So that gives me what I want in terms of making sure my multiplication is defined, and it's going to result in a 3 by 3 matrix. We'll talk about this in just a second. N times N, opposite order. So now that's a 2 by 3 multiplied by a 3 by 2. Yet again, the inner dimensions are defined, and so the outer dimensions give me the matrix that would result from that. So both of these multiplications would be defined. The question is, which one, if either, is actually going to give us what we want? So what's going to happen here is we're going to have to pay attention to the units. In other words, when I multiply these two together and I look at the dimensions that result in my answer, the units are going to go with those as well. So I have to think about, what do my rows, what do my columns represent? So say we do M times N. So the resulting matrix is going to have the rows in the first matrix and the columns in the second matrix. So my rows in my first matrix represent my nutrient types, so protein, carbs, and fat. And then my columns in my second matrix represent mix X, mix Y, mix Z, my different types of cereals. So the resulting matrix is going to have that type of label for the rows and that type of label for the columns. In other words, it's going to compare the nutrient contents versus the mix types, the different types of cereals. Well, that looks promising. That's more so what we want to compare. The question is nutrient type versus mix type, nutrient type versus mix type. This matrix would probably give us what we want. Let's look at the second one though before we just dive in and decide anything. So now we're doing N times N. So again, we're looking at rows by columns. Well, the rows in N represent ingredient types, and then the columns in M also represent ingredient types. So when we do the multiplication, those labels go with the resulting matrix. So it ends up being ingredients versus ingredients. What that essentially means is all the additional information we have about nutrients and mixture type will actually be eliminated if we multiply N times M. Well, those are the pieces of information we're interested in. We're interested in the nutritional value versus the mixture type. So multiplying N times M is not something that's going to give us the information we want. It's actually going to eliminate the information we want. So that means M times N is going to be the multiplication we want to do. It is defined, and it's also going to give us the combined information that we're interested in. So I'm going to take those two matrices in that order, and I'm going to multiply them together. Okay, so we have a 3 by 2, we have a 2 by 3, so the result is going to be 3 by 3. So across the row and then down each of the columns, that's going to give us everything in our first row. across the second row, down the columns, that's going to give us our second row, and then across the bottom row and down the columns is going to give us our bottom row. And I want to label the rows, I want to label the columns. So you might want to take a second, pause, make sure you can do this multiplication and you end up with these values. Keep in mind, you can do the individual multiplications in a calculator. That's not a problem. That's perfectly fine. These should be the particular elements you get. The labels are going to tell us what we're actually looking for at that point. So we were looking for two different values. We wanted the amount of protein in mix X. Okay, so I'm going to base what I'm looking for on my labels. So protein versus mix X. Well, protein represents our first row, and then mix X is the first column. So I'm looking for the intersection of that row and that column, which in this case is going to be the first element in my resulting matrix. So the answer is going to be 70, in this case 70 grams of protein in mix X. Now we also want the amount of fat in mix Z. So we're looking at fat, which is the bottom row, and mix Z, which is the third column. So third row, third column, where do they intersect? They intersect at the very last element. We have 30. So that's going to be 30 grams of fat in mixture Z. So this is just one way we can use matrix multiplication. We use it when we have sort of, I guess, layers of information. We have different things that are compared to one another. If we want to compare sort of across the dimensions, matrix multiplication can sometimes accomplish this for us.